The following sounds have been synthesized entirely from scratch. These patches emulate physical factors such as temperature and movement, and I've also simulated group behaviors and chorus sounds. If anyone wants to listen to the extended versions of these sounds, I've uploaded them to my Bandcamp, linked below. In this video, we'll learn how to design these sounds from scratch by exploring animal communication, audio analysis, sound production mechanisms, and synthesis. Furthermore, it might strengthen your mental fortitude, as insect sounds can get really annoying really fast, especially this one. I plan for this video to be the first part of a larger series about wildlife sound design. But for now, we'll start with insect sounds, as they can be some of the simpler nature sounds to replicate. And as a quick note before the video begins, I recently created a Patreon, where I've uploaded the Ableton project file for some of the sounds in this video. More about that later on. Now, before sound designing any creature, we should understand the purpose and mechanism behind its sound production. As we sound design organisms, we should consider if the sounds are purposeful or indirect, and whether they come from an individual species or multiple species. In this series, I want to explore the more purposeful sounds, including both individual sounds and group sounds. To be more specific, we should know what purpose our sounds serve. Are they for attracting mates, communicating with conspecifics, hunting, such as a bat performing echolocation, teaching skills as seen in birds, or other reasons? Asking these questions will give us more direction and help us mimic the behavioral aspects of sound. Furthermore, to prepare our sound design process, we should consider the region in which an organism produces sound and how it affects the sound. This region is called the active communication space, which may guide our sound design decisions. Let's look at the path sound takes in this space. For this, I'm referencing an incredible book on soundscape ecology, which I'll link below for anyone interested in understanding these concepts more deeply. The path consists of a sender and a receiver. At the start of this path, the sender creates sound via a sound production organ. This would be the first step when actually synthesizing the sound. The generated sound may then be modified by some anatomical structure before propagation. For example, our mouth, throat, and nose modify the sound produced by our vocal cords. This could be where you do any immediate processing to the sound, like filtering. Following modification, the sound propagates through space, eventually reaching the receiver. This space could be a forest, a cave, a desert, anywhere. This is important as it will give us an idea of what reverbs and other effects to use. For example, a cave usually has hard reflective surfaces, thus you may hear more discrete echoes as opposed to a forest, where the sound would be more diffused and absorbed. The propagation space also gives us an idea of how to contextualize our sounds. Going with the cave example again, we could include dripping sounds in the background to accompany our focal sound. Then there is sound reception, which in our case would be some imaginary listener or microphone picking up the sound. Thinking about where our receiver is in relation to the sender is necessary, as it will affect the processing we do in order to emulate the propagation space. Generally speaking, the closer the receiver is to the sender, the more loud and clear the sound is, as we don't hear the effects an environment has on the sound as much. There are many ways animals produce sound, and we'll explore different methods throughout this series. But given this video is specific to insects, I want to cover 3 methods specifically. These methods are stridulation, Tymbals, and vibration, which we will cover in the synthesis section. But before we start synthesizing anything, we need to learn what to listen for when referencing natural sounds. As we analyze various sounds and recordings, it's helpful to equip ourselves with proper terminology. For this series, the relevant terms are as follows. A call is a relatively short and simple vocalization, while a song is a long and complex vocalization, oftentimes made up of various calls. Even more specific to this video, some animal groups, like insects, use pulsation to make sound. In this case, a pulse train is the assortment of individual pulses making up a chirp or song. A pulse shape is the spectral shape of individual pulses. By spectral shape, I'm referring to the shape of its amplitude and frequency over time. A chorus is when many organisms make sound over a short period of time, which can be synchronous or asynchronous. Furthermore, a chorus can be composed of a single species or multiple species. And don't worry if some of these terms aren't super clear, as we will contextualize them throughout this series. For analyzing audio, I typically use 3 tools: waveforms, frequency spectrums, and spectrograms. When I'm observing the temporal features of a recording, such as the length of a sound, the time between sounds, the amplitude of a sound over time, and more, I'll use waveforms. The waveform in your DAW will probably work just fine for this. For getting a simple look at the harmonics of a sound, I'll use a frequency spectrum. Ableton has a decent spectrum built in. If you don't have a good spectrum analyzer though, the free plugin M-Analyzer is pretty good. When I start to do a more in-depth analysis of the harmonic and temporal attributes of a sound, I use spectrograms. I find myself using spectrograms most often as they can be quite detailed and they look cool. Isotope RX honestly has an amazing spectrogram, but Signalizer is one free alternative. Wave Candy is great if you have FL Studio, and Minimeters is also good as a cheap alternative. Once we have our preferred analyzers, we just need to know what to look for. The first thing I usually do is try to understand the sound's behavior. By behavior, I mean how the sound changes throughout time and what patterns occur and why. This is closely related to temporal analysis, but I like to think of it as a more intuitive and less rigorous approach to analyzing sound. Here's an example with the Katydid recording. One behavior I notice is that before each chirp occurs, there is a shorter, less pronounced sound. This pattern occurs with every vocalization in this recording. Moving on to temporal analysis, it's helpful to identify pulses and pulse trains and how their amplitudes change over time. Let's take this simple example of a cricket chirp sound. The chirp itself is the pulse train, which when we zoom in, we can see is made up of individual pulses. It's important then to analyze multiple chirps so we have more information to work with and observe how the amount of pulses in each pulse train varies. Then we can analyze how long each pulse is, how much time occurs between each pulse, and how long each pulse train is and how much time occurs between each pulse train. Furthermore, we should analyze the amplitude shapes of both pulses and pulse trains. Finally, we should have the ability to identify harmonics and pitch patterns. When analyzing a recording using a spectrogram or frequency spectrum, I first look to identify the base frequency, or fundamental. From there, I make notes about the harmonic relationship. Oftentimes, I'm trying to find out whether the harmonics are odd, even, or both. And if anyone is unfamiliar, harmonics are simply multiples of the base frequency. The first harmonic is the base frequency, the second harmonic is double the base frequency, the third harmonic is triple the base frequency, etc. If a sound has all integer harmonics, that is, both odd and even harmonics, then we could start recreating it using a saw wave, which also has all integer harmonics. If a sound has only odd harmonics, we could replicate it using a square wave or triangle wave, depending on how quickly the harmonics roll off. Aside from harmonics, we also want to look for changes in frequency over time. This will determine if and how we use frequency modulation in our sound design. Now that we have an idea of how to approach and prepare our sound design, we can start synthesizing some bugs. As mentioned earlier, insects use many forms of sound production, which include stridulation, Tymbals, and vibration. First, let's focus on stridulation. This is when an organism rubs body parts together to produce sound. In most cases, and in the examples we'll cover, this involves a structure with a hard surface called a scraper, which rubs against a comb-like surface called a file. Two iconic insects that use stridulation are crickets and katydids. Let's start with cricket sounds. Crickets perform stridulation with their forewings. Only male crickets stridulate as females don't have the necessary structures. In most cricket species, this involves a scraper on the left forewing striking a file on the right forewing. This process produces that iconic chirping sound. And to be exact, the tooth strike rate of the scraper across the file's teeth is equal to the sound's frequency. So, if the strike rate is 5,000 teeth per second, the resulting sound is 5 kHz. While crickets make sound for many different purposes, I'll focus on designing the iconic mating chirp sound. First, pick a reference sound to analyze. I suggest using a clear recording of an individual cricket chirping. I usually go to freesound.org to find reference sounds. In the reference I chose, the pulse trains, which are individual chirps, occur between 300 to 800 milliseconds, with 200 to 400 millisecond gaps between each one. The individual pulses within each chirp last only 15 to 20 milliseconds each, with the gaps between each pulse lasting for about the same duration. To get the pulse rate values I used later on, I converted from milliseconds to hertz. While analyzing the reference sound with a spectrogram, we can see the base frequency of the sound is at roughly 5 kHz, with two audible overtones at 10 and 15 kHz. Furthermore, there's an obvious frequency curve present in each pulse, which we can replicate using frequency modulation. Now that we understand the building blocks of this sound, we can begin synthesizing it. For this, I'll be using the synth phase plant. First, we can start with a saw wave at a base frequency of 5 kHz. A saw wave works because it contains both even and odd harmonics of the base frequency, which are present in the reference sound. And because only 3 harmonics are audible in the reference sound, we can low pass the saw wave after the third harmonic. Next, we can modulate the gain of the saw wave using a custom LFO shape, which mimics the volume shape of the cricket pulse trains. Let's call this the chirp LFO. I'm setting the LFO's rate based on the reference pulse trains. We should note that a cricket's chirp rate is a function of the air temperature, where higher temperatures result in faster chirping, as described by Dolbear's law. So, for extra realism, we can create a macro that controls the rate of this chirp LFO. We can call our macro temperature and make higher values result in quicker chirp rates by adjusting the modulator rate. Because Dolbear's law describes a linear relationship, you shouldn't have to do any remapping for this macro to be fairly accurate. Note that Dolbear's law can vary slightly between cricket species, so if you're wanting to be precise, be sure to research the species you're referencing. It should also be noted that temperature has an impact on many insect sounds, which we will see more of later on. To create the pulses, we can use audio rate modulation. This is because the pulse rate is above 20 Hz. First, let's make the volume shape of each pulse with a custom wavetable. In Phase Plant, you can do this by using the wavetable oscillator and opening up the wavetable editor. Try to emulate the volume shape of the reference pulse. Here's what mine looks like. Now, set the harmonic to 0 and use Shift to dial in the pulse rate. Remember that in the sound I analyzed, the pulse rate was about 25 to 30 Hz. So I'll set the shift value between 25 and 30. Now modulate the level of the saw wave all the way using the wavetable oscillator, like so. Cool. Now we can move on to creating the pulse's frequency curve by modulating the frequency of the saw wave. We can use the same process that we just did for the volume shape, just that we want to mimic the frequency curve instead of the volume shape in the wavetable editor. Again, set the harmonic to 0 and use the same shift value as your other wavetable. Now, modulate the shift value of the saw wave with this wavetable. In my patch, I set the modulate amount to about 40%. For additional control, you can map the shift values of the wavetables to a macro to control the pulse rate. While that does it for almost the entire sound, we should create some subtle nuances. We can do this simply by using slight random modulation on various parameters in the patch. In my case, I randomly modulate the pitch of the saw, the levels of each wavetable, and the shift values of each wavetable. Again, this modulation is very subtle. Also, make sure if you modulate the shift values of each wavetable to use the same modulator and to modulate by the same amount each, otherwise they will fall out of sync. That just about does it for the individual cricket chirping sound, but oftentimes you hear a cricket chorus instead of an individual cricket, so how do we go about that? When doing an insect chorus, my approach generally works like this. I start by creating a few parallel chains of the cricket chirp generator, with each chain having very subtle differences in timing and pitch. Essentially, each chain acts as an individual cricket. I then try to put each cricket in a different location in respect to our imaginary listener. I do this first by using a subtle Haas effect in each chain, so that the cricket sound reaches one ear before the other, which I then emphasize a little more by panning the chain accordingly. The further I imagine the cricket to be, the more filtering and reverb I use. For filtering, I simply use high shelf or low pass filters to dampen the sound, and for reverb I use a mix of convolution and algorithmic reverb by using Ableton's hybrid reverb. I also have two chains acting as really distant layers to give more depth to the chorus. For those who watched my tutorial on water sound design, you can try using the stacking technique I discussed in that video to make an even more dense chorus. Lastly, after reading up on cricket group behavior, I found some interesting details on how crickets make sound based on their proximity to one another. In short, a study done on field crickets demonstrates that crickets 1 meter apart sing in a more synchronized chorus, with the chorus becoming less synchronized the further they are from one another. However, at distances less than 1 meter apart, the males become less likely to sing when another male is already singing. So I simulated this in my cricket rack by creating a macro for proximity. As the proximity macro increases above a certain value, it increases delay times within each chain so that the chains become less synchronized with one another. Conversely, as the macro goes below a certain value, it reduces the volume of the chains except for one. If you wanted to make it more realistic, you could have it so that it's not the volume of the chain being reduced, but rather the probability of MIDI notes being sent to each chain. So that covers everything for the cricket sound. Now we can move on to katydids. However, to save some time, I will spend less time talking about how I analyzed the samples beforehand and just focus on the synthesis aspect. Katydids make a variety of sounds, from fluttering sounds to loud chirps. For this project, I chose to recreate their iconic song chorus. I started by creating the individual chirp, which can be a bit difficult to get sounding right. Again, I won't go into detail on the analysis for the sake of time, but know that I approached this sound in the same way I approached the cricket chirp. I started with a bass frequency of roughly 3.6 kHz, with two overtones at 5.2 kHz and 6 kHz. I'll refer to this group as the tone group. I then made a custom wavetable which mimics the pulse shapes in the reference I chose. I did this by drawing a waveform at frame 1, and then another waveform at frame 256, which is similar to the first frame, just with a wider pulse width. I then interpolated between those two frames to create the wavetable. I did this because I noticed that in the reference sound, when the pulse rate changed, so did the pulse width. I set the wavetable harmonic to 0 and the bass shift value to 230. Then I fully modulated the level of each generator in the tone group using the wavetable. and to avoid aliasing distortion, I put a high pass with a cutoff a little before the bass frequency. To recreate the pulse trains, I made one custom LFO to modulate the volume, and another to modulate the shift and frame values of the pulse wavetable. And because Dolbear's law also applies to Katydid chirp rates, we can map a macro to the LFO rates to control the chirp rate. Finally, to create more frequency content, I bandpassed a noise generator and modulated the level using the pulse wavetable. And again, to polish the sound, I used some random modulation to create subtle variations. To generate the chorus sound, I essentially used the same setup the crickets had, but with some differences. The first difference being that I have a legato note being sent to an arpeggiator, which acts as a trigger for each call. I then delay the MIDI input randomly by using a note delay max device. The other difference is in the singing behavior. Like the crickets, their chorus is synchronous. However, when there are a lot of katydids in a particular region, the song becomes antiphonal. This is to say that two groups alternate between singing, and the katydids within each group still synchronize their song with the group. So I simply replicated this by making two chain groups with one group being delayed, by placing MIDI delays within the chains. And again, each chain acts as an individual. With these examples of stridulation out of the way, I want to move on to another kind of sound production, that being timbal-based sound production. For this, we'll learn to recreate the sounds of cicadas. Male cicadas produce their songs using specialized sound organs, called tymbals. They are located on each side of the cicada's abdomen with an air-filled cavity between them, which amplifies the song. To be more specific, a line of stiff ribs embedded in the timbal are buckled sequentially. This buckling generates resonant clicks, and can be repeated rapidly at several hundred times per second. So, I centered my cicada sound design around this process, by creating a patch where I can control the rate of synthesized resonant clicks. The awesome thing about this system is that we can imitate several behaviors just by the way we modulate the click rate. I started by structuring the tonality of the click using a noise generator and a saw wave at 4.6 kHz. I then high-passed the click group at roughly 400 Hz and then again with the nonlinear filter at 4.5 kHz. Also, I wanted to make a macro for loudness later on, which I wanted to affect the tonality of the click instead of only changing the volume. So I made it early on and mapped it to the slope of the noise, and made it such that when the loudness macro lowers, the noise slope gets closer to that of brown noise. Given the click sounds can be defined as individual pulses, I wanted to make a custom wavetable for the pulse shape of the click. And just like the Katydid sound, I drew two waveforms at opposite ends of the wavetable to control pulse width, which I interpolated between using the waveform crossfade button. I set the harmonic to 0, the shift value to 10 Hz, and then I used the wavetable to modulate the noise and saw levels. I then mapped the loudness macro to the level of the pulse wavetable, and to control the click rate, I used a new macro and mapped it to the shift value of the pulse wavetable. And I made it so that at maximum it increases the shift value to around 160 Hz. Earlier in the video, I talked about modification, where a generated sound may be modified by anatomical structures. In the case of our cicada, the air-filled cavity between the tymbals along with the timbal organ itself are such structures that modify the click sound. So, to shape the resonance of the click even more, I used the resonant high-pass filter along with the filter table. If you want to add some variation to the resonance, you can randomly modulate the cutoff value of the filter table. Then, I wanted to make it so that at lower click rates, there are noticeable pulse trains. So, I implemented this by creating an LFO which is mapped to the gain of the click group. Then I mapped the click rate macro to the depth of the LFO, so that at higher values the LFO depth is lower. As the LFO depth lowers, I want the click group's gain to sit at a constant value, so I mapped the click rate to a remap, which starts increasing the gain of the click group after a certain click rate value is reached. I also wanted to widen the pulse width after a certain click rate value, so I mapped the click rate to another remap, which modulates the frame value of the pulse wavetable. Finally, to polish the sound, I mapped another macro to a frequency shifter to give me more control over the sound's tonality. And as usual, I introduced some variation to the sound by randomly modulating various parameters. To simulate different behaviors, we can modulate the click rate in different ways. It's pretty fun to mess around with. For the chorus, I again set it up similarly to the cricket chorus. I have a few chains dedicated for the ambient chorus sound, a couple for closer cicadas with noticeably different behaviors, and a layer of stereo noise which is bandpassed around the same resonance as the song. Temperature also affects cicada singing, such that at higher temperatures the clicking is louder and more frequent, and vice versa. So, you can make a temperature macro mapped to the loudness parameter we set up earlier in each chain, and you can also map it to the depth values of modulators that modulate the click rate parameter. That covers just about everything for the cicada. So now we will explore the last sound production mechanism I'll cover in this video: vibration. Vibration involves the rapid movement of wings or other body parts to produce sound. One iconic example of vibration is the annoying buzzing sound produced by flies. As flies flap their wings, they emit sound containing a series of harmonics. The rate of a fly's wing beating depends on the species, size, and age, but generally it's around 200 beats per second, which produces a fundamental at around 200 Hz. I started synthesizing the fly with a saw wave at a base frequency of 190 Hz. I then opened the harmonic editor and changed the amplitudes based on my reference sound. I made the first, second, and fifth harmonic the loudest. I slightly low-passed the wavetable at 10 kHz to make the sound a bit softer. Then I bandpassed a white noise generator and made the gain very quiet to give the sound some subtle noise. And more importantly, I also used the noise output to slightly modulate the level of the wavetable. I noticed some of the harmonics disappearing and returning in my reference sound, so I simulated this by randomly modulating a notch filter after the wavetable. And honestly, you can modulate any kind of filter here to introduce some movement to the sound, so feel free to experiment. The wing beat frequency of a fly varies over time based on how it navigates and reacts to its environment. So I simulated this by randomly modulating the shift value of the wavetable. This modulation should be subtle, and I have mine being modulated by only about 0.5%. I used two modulators, one for slower variation and one for quicker variation. I also randomly modulated the amplitude of the sound in a similar manner with slower and quicker variations. For the larger fluctuations in amplitude, I'm remapping a random modulator to only output some values, which then controls the depth of a random modulator, which modulates the sound's gain. This makes the larger fluctuations a bit more rare and noticeable. Following this, I introduced more movement to the sound using an ensemble, with random motion and with only two voices. Finally, I polished off the sound with some filtering and distortion. Now, to make the fly actually move through space, you'll want something that not only simulates distance, but also the Doppler effect. Flying insects can move anywhere from 2 to 15 meters a second depending on the insect, which in many cases will cause a noticeable Doppler effect. For this, I'm using a Max device my friend made, which isn't public, but you can use the free Max device ml.distance Doppler, linked below. I'm not aware of any free VST plugins that do this in the same manner, but if anyone does, please let me know in the comments and I'll link it in the description. From here, it's pretty easy to create the sounds of other flying insects like bees or mosquitoes. You can simply adjust the shift value of the wavetable based on the wing beat frequency of the insect you're referencing and adjust the harmonic amplitudes. But what about swarm sounds? For this, I'll share my process for sound designing a bee swarm. I started, of course, by making the individual bee sound, which is simply the fly patch but with a shift value of 255 Hz instead, along with some modulation changes. My general idea behind the swarm system was to create a few layers dedicated to the dense swarm sound, with additional layers that simulate individual bees which are closer to the observer. Let's look at the close layers first. The first layer is just a filtered version of the individual bee sound, with an ensemble set to 16 voices to blend in with the rest of the swarm. The next two layers are similar, but they are not as heavily filtered, and they have a somewhat gross distortion. They are also quieter than the first layer. Each of these close layers include the Max device I mentioned earlier for simulating movement. The next 6 layers act as the bulk of the swarm sound. Given each of them are fairly similar to one another, let's focus on one layer. It uses the individual bee patch but with some modifications, with the first change being a slightly lower shift value. For the ensemble, I'm using 14 voices, and I'm randomly modulating the detune and spread values. I removed the phase distortion I had in other patches, and instead distorted it using Ableton's saturator. I filtered it to boost the high end and make the sound a bit more harsh overall. The other 5 layers are essentially identical to this one, with the trick being that each layer has a pitch shifter in it with a slightly different value. I should clarify that these layers don't have any device for simulating movement, as they're meant to be an accumulation of thousands of bee sounds. And to polish the sound, I have some randomly modulated noise layers, which are high-passed to give more character to the high end. And with that, we've explored all of the insect sounds I wanted to cover in this video. I hope this video serves as a resourceful guide, or at the very least, inspires you to make some sounds. I do all of the research, sound design, 3D modeling, editing, and music for these tutorials, with the exception of my friend Lukasipo providing some additional background music for this video. So, of course, it's a lot of work, and if you wish to support me, you can do so either on my Bandcamp page or through my newly created Patreon, linked below. I've uploaded the project file for some of the sounds in this video, namely the cricket, katydid, and cicada sounds, on my Patreon, and I plan to share a lot more projects, behind the scenes, samples, and walkthroughs on there. But that's all for now. Thanks for watching.